I'd like to now introduce Spencer O'Reilly, and he's going to continue this sort of metamaterial 3D printing using the makerspace to do physics research and to do 3D printing of a different metamaterial. And the thing I most want to say about Spencer is, well, Tom mentioned it earlier that students at some point, own the project, and Spencer did that immediately. So, last week, Scott and I had a discussion where, I said to Scott, have you been directing Spencer? And he said no, and he asked me, and I said, no, I really haven't been directing Spencer. And every time I would like at night, I'd realize, oh yeah, he's going to have trouble with this problem. And I would go to him the next day and say, how have you got to that problem yet? And he said, oh yeah, no, I did that 2 weeks ago. I'm through with that. And so he just, he owned it like no other student I've seen. And this is truly his research completely. It was.
Go me, I guess. All right, so as mentioned, I'm Spencer O'Reilly, and I'm going to be talking to you about 3D printing of metamaterials with negative thermal expansion, which I know is a little intimidating, but it's really not that many. So first I want to talk to you just about thermal expansion. It's a pretty common phenomenon. It's very well documented, and we all kind of know about it, even if you don't really know exactly what it's about. So start with just a thermometer. They work with thermal expansion. When a thermometer heats up, the mercury in it expands and gets higher. That's thermal expansion. Also, you can see right here, there's these little gaps in bridges so that when the bridge heats up in the summertime, it can expand and won't degrade the quality of the actual bridge itself. So when you're on a bridge and it's like dun 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 dun, that rhythm, that's little gaps in the bridge allowing for space to thermally expand. It's also very common in train tracks. So that's what that like dun dun dun. And so, yeah, right. Yeah, so that's a little bit about thermal expansion. Talk a little bit more. There's positive thermal expansion and negative thermal expansion. Positive thermal expansion, it again describes an object's volume as related to temperature. So as an object heats up, it expands and gets larger. It's ruled by this law right here. This is the equation for linear thermal expansion, where it's the change in an object's length is equivalent to its thermal expansion constant. That depends on the actual material itself, the initial length, and the change in temperature. So now my goal is negative thermal expansion. I want to build something so that when it heats up, it contracts instead of expands, like most things do. And then just lastly, metamaterial. I got this from Google, just a little It's a little explanation of what it is. It's a synthetic composite material with a structure that exhibits properties not usually found in natural materials. So basically, it's a man-made structure that is made to do something that nature doesn't want to. So the theory behind it is, it comes from the design of a Hoverman sphere. I forgot to bring it, but you know those little toys you had as a kid where you pull them apart and it's this little ball and it expands? The design for this structure comes from that. Materials being used are polylactic acid and steel, and my structure, the area will contract instead of the volume as such in this picture. So here's the design for the material. Like I said, I'm going to be using two materials. Material one is going to be these little rods in here, and there are two distinct characteristics that both materials need to have. The first material needs to have a high thermal expansion constant so it can expand when it's heated, as I talked about before. It needs to be very, very rigid so it can push on that kind of shell material. Material two is going to be that shell material, which is this dark kind of shell that I talked about, as I said. And then the two characteristics that needs to have is it needs to have low thermal expansion so it does not expand when heated, and it needs to be very elastic so that material one can push on it, and it will allow the entire structure to contract. As these expand, everything will kind of push into itself. So here's my first design in Tinkercad. Tinkercad is the software that I used for 3D printing. So this is the overall structure. You know, it looks very similar to the design that I pointed out. And this is going to be the shell material. This is going to be material 2. So this is going to have a low thermal expansion constant, and it needs to be somewhat elastic, as I mentioned. So here's the first print. It came out pretty well. What I found that it had too many diamonds in it, and it was really hard to contract. There were also some imperfections down here, but when you took the structure and kind of push on it with your hands, you couldn't really contract it very well. It didn't want to move in. It's very rigid, and the walls were a little bit too thick. So I went back to the drawing board, second draft in Tinkercad. This one has a lot less diamonds. I added these little grooves that are kind of hard to see, but I added these grooves so that the rods of material 1 could stand in there very nicely. And I also made the walls much thinner so that it's easier to contract. So when you took this one, you pushed in on it with your hands, you could actually see it. You can feel it contracting and see it contracting. So this is how the second print came out. It came out really, really well. This was the print that I used for most of the project. As I mentioned, it had thinner walls and less diamonds, so it was much more easy to contract. The new grooves really helped with holding in the rod material, and there were a lot less imperfections because it was just a simpler print. So for my method of testing, I put the structure on a hard, flat surface, much like a desk like this, and I put a camera and a hairdryer at fixed points. And I would turn the hairdryer onto high and point it down at the material and take pictures continuously as the structure heated up. And I would also have a thermometer there so I could know how hot it was getting. So on the iPhone camera, which is the camera that I use, there are 19.37 pixels per millimeter. And what I would do is I would take all these pictures, download them onto my computer, and then go look at the pictures individually as it was heating up. So I would measure the number of pixels across the diameter and divide by this number of pixels, 19.37, and that would give me the millimeters and the distance of the diameter. So, quick example, if there was 1,700 pixels on the image for the diameter, you would take 1,700, divide it by 19.37, and you get 87.77 millimeters. So that's how you measure the distance without having to use a ruler or anything obstructing the heat flow into the structure. So here are my results. This is the structure at 20 degrees Celsius. This is just room temperature, what I started at. This is no heat added. I measured 1,715.02 pixels. So the initial diameter is 88.54 millimeters, and that number comes from dividing that number of pixels by 19.37. As I started to heat it up, you can see that the diameter gets smaller and smaller at 25 degrees Celsius, 35 degrees Celsius, and 45 degrees Celsius. You can see the thermometer here, so you can actually see how hot it's getting, and you can notice that heat is being added to the structure. And so here is the final structure I could get, because PLA, the shell material, melts at a very low temperature, so it just morphs and just kind of like folds into itself, and the rods make it all deformed. So this was right before it all got messy. This was the best. This was the last good picture, yeah. And so this is 47 degrees Celsius. You can see up here. And I measured 1,695.84 pixels across. So that means that the final diameter is 87.55 millimeters. So I saw a difference of 0.99 millimeters, or I guess 1 millimeter. So in conclusion, the difference in diameter I saw, again, was about 1 millimeter. That's really good for something that only was heated 27 degrees Celsius. So from this equation here, we can see that I designed a material with a thermal expansion constant of negative 0.00414 per degree Celsius. So those are just the units that are associated with the constant. So yeah, it was a success. I created that. I did it. Credit to me. So there's a lot of further research to be done with this, even though I did it. So the first thing is that material 2, the shell material, can be experimented with. As I mentioned, PLA melts at a very, very low temperature. So materials with higher temperature and maybe lower thermal expansion can be experimented with to see further results and maybe a more dramatic shift in that diameter. Also, changing the structure of material 2, as in the diamonds and the length and the width of the wall, can help a lot with contraction. And then finally, material 1, the rods, can also be experimented with. You can experiment with how rigid the material is and also kind of the thermal expansion constant there. Try to find a happy medium between those two. And that is the further research that can be done on this project. So finally, I want to thank Dr. Jones in the back for guiding me through this, because I did need help even though he said I didn't. But yeah, that's all.
questions for Spencer?
Is that the only design that you can make where it has a negative thermal expansion, or are there other slogans?
That's an interesting question. This is the paper that I did most of the study on, and when I read that, they really just talked about where it says Hoberman sphere inspired. So that is the only one that I know of currently. I know that there are some materials in nature that have negative thermal expansion constants. They're just super rare and hard to work with. And Dr. Kaminsky, do you have a question?
So what got you interested in this subject in the first place?
I don't know. I kind of wanted to do something that wouldn't be very scientific heavy, like super, like I'm talking and you're not understanding what I'm saying. So this was something that was, yeah, right. This is something that I knew I could present to people who are not STEM majors and people who are not very heavily invested in science and could talk to them about very easily and have them understand it. Because it's, again, not a very hard, not a difficult topic.
Okay.
All right.
Yeah, thank you.